So good evening, Wolverhampton, and a happy new year to you all. This is the end of everything. About 3 years ago, I gave you a talk, The Beginning of Everything, about how the universe came to be. This is the bookend to that talk, telling you how everything will come to an end. So, in a sense, we're going with Buzz Lightyear to eternity and beyond. I'll be giving a short prologue, and then we'll be looking at the future of the Earth and the Sun and the solar system, and then the far future of what's going to happen to stars and galaxies, and then we'll be looking into the far, 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 far future and the ultimate fate of the universe. And then, so as to leave you not too depressed, I'll have a little epilogue at the end. So, I'm not going to remind you of what I said 3 years ago, other than we reckon that the universe came into being some 13.8 billion years ago, and given that the universe is expanding, presumably everything used to be a lot closer together. And we believe that everything that we now see in the entire observable universe used to be separated by just centimetres, if you go back far enough in time. So in the very early universe, the universe made all of the hydrogen and the helium, which got dispersed throughout the universe, and the hydrogen, of course, made the stars and the galaxies. In this talk, we're going to be looking into the future, and I'll be using this timeline across the top here. Each small box represents 10 times further into the future. And so we'll be looking, for instance, 1,000 years into the future, 10 to the 6, a million years, 10 to the 9, a billion years, 10 to the 12, a trillion years into the future. So that red box is simply a way of reminding us where we are on this timeline so that we don't get completely lost. And I must credit Adams and Laughlin, who published a paper some 25 years ago, in which they laid out the timescales on which many astrophysical phenomena are likely to occur, and I've used that to try and get all my slides in the right order. So I might be jumping around between what's happening to the Earth, what's happening to the Sun, what's happening to the galaxy. I'm trying to do it all strictly in time order. So I'm not going to start in 10 or 100 years from now. Let's assume that we get climate change under control. Let's assume we don't start World War III. Various things are going to happen in the relatively near future. One of them we know is that the Earth is going to continue slowing down because of the tidal tug of the moon. If we want to keep our clocks synchronized with the rotation of the Earth, then every once in a while we have to add a leap second. At the moment, we've been doing it once every few years. But in 1,000 years or so, the Earth will have slowed down in its spin, and leap seconds, if we want to continue synchronizing our clocks, will need to be added every few weeks. There are various things that are going to happen where we can't really say what the timescale is. We know some stars are going to go supernova, but we really don't know when. By comparison, predicting what's happening with the Earth is a little easier. For instance, we know that the Earth's axis precesses in a large circle once every 26,000 years, as indicated by this cartoon on the left. That means the axis of the Earth effectively maps out a big circle on the sky. At the moment, the Earth's axis is pointing towards close to Polaris, within a degree or so of Polaris. But in another 12,000 years or so, it will have pointed towards Vega, on the other side of this large yellow circle. So that's going to make it easy for Boy Scouts to point out north. They just look for a really bright star, that's probably Vega, that will tell them which way is north. But apart from making it easier for Boy Scouts, there are other consequences of the pole star changing. At the moment, Polaris is such that when we're pointing at Polaris, the Earth is closest to the Sun, i.e. at perihelion, during northern winter, because when we're pointing at Polaris, that means that we are in the winter phase of our seasons. Whereas you can see from the cartoon on the right, if the Earth's axis is pointing towards Vega, that means we'll be closest to the Sun when the northern hemisphere has its summer. That means instead of the seasons being mitigated by the distance and the tilt, they're going to add together and give us more extreme seasons. Now, variations in the Earth's climate that are due to either changes in the Earth's spin or changes in the Earth's orbit are collectively known as Milankovitch cycles, and we'll hear that again shortly. On a timescale of 10 to the 5 years into the future, the Voyager spacecraft are going to pass through other star systems. The Voyagers, if you remember, were launched in the late 1970s, a few weeks apart. Voyager 1 went to Jupiter and Saturn. Voyager 2 continued on to Uranus and Neptune as well. So Voyager 1 is heading out of the solar system at the top here and is heading off in the direction of the star system Gliese 445. Voyager 2 at the bottom of this graphic is heading off in the direction of the Ross 248 star system, and they are likely to pass through these star systems on a timescale a little less than 10 to the 5 years. Also on this diagram we see the Pioneer spacecraft. They were launched a few years earlier, but they're actually moving more slowly, so it'll take them a little longer to reach the nearest star systems. Pioneer 10 on the right of the screen is heading off in the direction of Aldebaran. Pioneer 11 on the left of the screen is heading off in the direction towards the centre of the galaxy. Still on a timescale of 10 to the 5 years into the future, we know that an ice age is coming. The historical record tells us that we have repeating cycles of ice ages that occur on timescales of order 100,000 years or so. That's a consequence of changes to the Earth's orbit around the Sun. We know that Earth entered a relatively warm interglacial period relatively recently, and so we know another ice age is due on a timescale of order 100,000 years or so. This is another manifestation of Milankovitch cycles, in this case the orbit of the Earth rather than the spin of the Earth. Still on a timescale of 10 to the 5 years into the future, the Earth will continue to slow because of the tidal tug of the Moon. And as I said earlier, at the moment we're adding a leap second every few years to keep our clocks synchronized with the rotation of the Earth. On a timescale of 10 to the 5 years, we would need to add a leap second every day. In other words, the rotation period of the Earth would no longer be 24 hours relative to the Sun. It would be 24 hours plus 1 second. It would have slowed down to that extent. Still on a timescale of 10 to the 5 years into the future, we don't know, as I said earlier, when stars are going to go supernova, but it seems quite likely that sometime in the next 10 to the 5 years, Eta Carina will probably go pop. The outer part of this star, the outer atmosphere of the star, has been shrugged off into the interstellar medium for thousands of years, producing the nebula that we now see in this Hubble picture, which was an astronomy picture of the day a few years back. So we know the outer parts of this star have been blown off into the interstellar medium, and that's probably a sign that this star is not too far away from going supernova. It might be beaten by Betelgeuse. Here's an astrophoto taken by an astronomer in Prague who's taking a picture of the night sky and then artificially brightened how bright Betelgeuse would be. Perhaps you recognise most of the constellation of Orion here, which is of course getting rather spoilt by a very bright shoulder there. But if Betelgeuse does go supernova at a distance of 600 light years or so, it will be very bright in the night sky and possibly even visible during the day. But many stars, as they approach a supernova phase, might go through a Wolf-Rayet phase. This is a particular type of star, and this is an artist's impression of Wolf-Rayet 104, which is about 7,000 light years away. And although supernovae are very powerful explosions, if not quite the right word, but that will do for the time being, it might be that the death of a Wolf-Rayet star might be even more dramatic than a simple supernova. The death of Wolf-Rayet 104 may result in a radiation burst more powerful than a supernova, because rapid rotation of these systems produces jets via a mechanism that we don't fully understand. And when this star dies, if one of those jets happens to be pointing in the direction of Earth, then it could be a threat, even at a distance of 7,000 light years, even 10 times further away than Betelgeuse. the death of one of these stars could be a problem if that jet is pointing in our direction. The gamma ray burst that results could, in principle, destroy life on Earth. If we move forward to 1 million years into the future, in the last few years the Gaia spacecraft has been mapping out the positions and the velocities of lots of stars in the Milky Way. And from that we can judge whether or not any of our neighbouring stars are likely to come close to us in years ahead. And it's been predicted that a particular star, Gliese 710, is going to come very close to us in about 1 million years' time. It's going to get close enough such that it will actually enter our Oort cloud. And the Oort cloud, being a large collection of very loosely bound icy particles, they are gravitationally bound to the Sun, but only very loosely, so the appearance of another star in our solar system will disrupt the Oort cloud and almost certainly send a lot of these particles hurtling into the inner solar system, where we will see many of them as comets. It's been predicted that we will perhaps see naked eye comets every month for perhaps 1 million years when Gliese 710 comes close to our Oort cloud. It's interesting to note that for a little while our solar system will actually have 2 suns in it. Admittedly, one large one in the middle and a rather smaller one further out, but we will have 2 suns, just like other systems that we all know about. This picture of meteor crater, still on a timescale of 10 to the 6 years in the future, perhaps that's indicating that we can expect one of these impacts every 1 million years or so. Well, no, that's not really why this picture is there. The picture reminds us that wasn't it really lucky that this impact just missed the visitor centre in the foreground? But it also reminds us that impacts on Earth get erased by weathering. So any impact crater that's more than perhaps 1 million years old, this particular one is relatively young at only tens of thousands of years old, but if a meteor crater was created more than 1 million years ago, it would be very difficult to see because of the weathering on Earth that would destroy any evidence of the impact. You might say that's characteristic of the Earth's weathering systems, but it wouldn't be true of any features that we see, for instance, on the surface of the Moon. Well, not quite true, because if we think of, for instance, the Apollo footprints, they are being eroded, not by weathering systems, the wind and the rain, as it would be on Earth, but the Moon is constantly bombarded with micrometeorites, and that is pulverizing the surface of the Moon and hence eliminating any signs that we have visited. Eventually, even the Apollo hardware itself will be erased under the impact of these micrometeorites. If we move forward to 10 to the 7 years into the future, 10 million years hence, the plaque that's on the Pioneer 10 and Pioneer 11 spacecraft, shown here on the left-hand side, that is eventually going to become too pitted and eroded to be able to see what the message is. The idea is the message says, this is who we are. The pulsar map on the left tells you where the spacecraft came from, and the little cartoon at the bottom says we came from the third rock from the Sun. But even though you think of the interstellar medium as being virtually a vacuum, there's still a lot of stuff out there. There's a lot of bits of dust, only tiny bits of dust, but after millions of years ploughing through it, the plaque will become pitted and eroded to the point where it won't be possible to read any information. So remember, Pioneer is going to be visiting stars on a timescale of tens of thousands of years. So after 10 million years, it will have had the possibility of passing through hundreds, if not thousands, of different star systems. If it's picked up in that time, then anybody picking up the spacecraft will be able to interpret the plaque. After 10 million years or so, anybody that does pick up the Pioneer spacecraft will not be able to tell where it came from. On a timescale of 10 to the 8 years into the future, we can ask what's going to happen to Saturn's rings. But perhaps it's worth asking the question first, where did they come from in the first place? It's thought that maybe a moon like Mimas, if it was pulverized, would produce enough dust and icy particles to form a ring system. And when you look at Mimas, you might think to yourself,
that's no moon. It's a space station.
Because it does seem to be something that's had a severe impact in the past. And simulations have been carried out where if you take a moon about the size of Mimas, ignore all of the other moons in the system, take a naked Saturn and a single moon, pulverize the moon, and then see what happens to the debris. You might think that the debris would simply move as a cloud around Saturn and take ages to spread out into a ring system. But in fact, a ring will start to form very quickly. Look at the timescale in the bottom right. It's only a matter of days or weeks before a ring system starts to form. And that's because within the debris cloud, all of the tiny little bits of debris will interact with each other, they'll keep colliding with each other and spread around the orbit of the original moon. Because they are still interacting with each other, all of these particles are slowly drifting inwards. And if we fast forward from when the rings were made to what the rings look like now, we see that they've actually migrated inwards towards the planet and are continuing to do so. So Saturn's rings only look like that for the moment. Eventually, all of the particles will continue to migrate inwards and will eventually rain down on the surface of Saturn, and the ring system will be no more. So for those of you who enjoy the view of Saturn through a telescope, get in now, because you've only got 100 million years or so before they disappear. Still on a timescale of 10 to the 8 years into the future, we have to remind ourselves that the solar system, predicting what the solar system is going to look like, is actually quite tricky. We might build ourselves little orreries or tellurians to tell us how the moon goes round the Earth and the Earth goes round the sun, or how the various planets move around the sun. But on this timescale of 10 to the 8 years, the solar system is actually chaotic. We cannot predict with any degree of certainty where planets are going to be. We can't even predict how many planets there will be. It might be that at some point in the future, Jupiter decides to eject one of the other planets in the solar system. Just like things have changed over past billions of years, and the solar system now does not look the same as the solar system of the distant past, the same is true of the future. It will change, and we cannot predict how it will change, because it is ultimately, like the weather, a chaotic system. On a timescale, again, of 10 to the 8 years into the future, we know that the Milky Way is rotating and the Sun is going around the centre of the Milky Way on a timescale of order 10 to the 8 years. We have a number of different spiral arms in the Milky Way, and as the Milky Way rotates, the Sun is going to move from where we are at the moment, which is a relatively low density region between spiral arms. We are going to move into a higher density region within a spiral arm itself. And the consequences are that we are going to have many more stellar neighbours. What does that matter, apart from a few brighter stars visible in our night sky? Well, having more stellar neighbours will have at least two consequences. One we've already mentioned. We know, for instance, that Gliese 710 is going to get close to us, it's going to interact with particles in the Oort cloud, and it's going to send a whole load of comets and asteroids our way. Well, if we have more stellar neighbours in 100 million years' time, we're going to have much more likely interactions with some of our close neighbours. And if we do have a large number of asteroids and comets coming our way, then it is possible that we will suffer extinction level events. If we look here, this graph is telling us how many species have been exterminated over the past 500 million years or so. We see a number of spikes, half a dozen spikes over the last 500 million years. In other words, not regularly, but roughly once every 100 million years or so, we get mass extinctions. The last one on the right-hand side, the KT, the boundary between the Cretaceous and the Tertiary periods, that's the one that killed all the dinosaurs. So we know that these things are likely to happen, and we can predict, not exactly when it's going to happen, but we can predict that it's more likely to happen on a timescale of order 10 to the 8 years into the future when we move into a spiral arm of the galaxy. This, of course, is just an artist's impression of a large rock heading towards, well, it appears to be heading towards Italy, as far as I can tell from the image. Now, that's bad news for Italy, but of course it will be bad news for the entire Earth if the rock is large enough. Species will be exterminated. The only real question is, will one of those species include us? Another consequence of moving into a spiral arm and having lots of stellar neighbours, apart from the increased threat of asteroid impacts, having more stellar neighbours means that there's a greater chance that one of our stellar neighbours is a supernova. At the moment, there are no really massive stars close to us. There are no supernova candidates close. But in 10 to the 8 years, when we have a lot more stellar neighbours, perhaps one of those close stellar neighbours might be a supernova candidate. A supernova within 100 light years of Earth would be a danger to Earth. It's been calculated that a supernova within 20 light years of Earth might conceivably end all life on Earth from the radiation that it produces. And if that sounds rather alarmist, bear in mind that we have evidence that there have been supernova within 100 light years of Earth. The supernovas generate a particular isotope of iron called iron 60, which doesn't occur in nature. And that has been found in Earth sediments. And this particular isotope decays or changes into other elements over millions of years. Iron 60 changes into cobalt and then changes into nickel. So if we look in the Earth's sediments and we find some iron 60, given that its half-life is millions of years, it can't have been around since primordial Earth. It could only have arrived relatively recently, and a supernova is the only known mechanism by which iron 60 can be generated. So, given that we know it decays into something else, anything we see in the Earth sediments must have arrived relatively recently. And that's how we know that supernova relatively close to us, more distant supernova, wouldn't have produced enough iron to actually be measurable within the sediments of the Earth. So we know it has happened, and we think it will happen again. The distance to the moon will continue increasing over these 100 million years that we're talking about. So through tidal friction, the moon will continue to rob the Earth of some of its angular momentum, some of its spin, and hence it will slow down the Earth and increase the size of the moon's orbit. There's an angular momentum exchange, if you like, between the Earth and the moon. At this point in the future, the length of the day will be some 25 hours. We'll have to give up the idea of leap seconds completely. Maybe this would be a good time to decimalize the clocks and talk about 100 units of time, which we used to call 15 minutes, for instance. But because the distance from the Earth to the moon is increasing all of this time, it won't be long before the distance to the moon is so large that there will be no more total eclipses of the sun. At the moment, we have this lucky coincidence that, as seen from the Earth, the disk of the moon is quite often just large enough to cover the disk of the sun if they are aligned with each other. But in the future, because the moon will be further away, the apparent size of the moon's disk will be too small to cover the disk of the sun. So we will no longer ever get total eclipses of the sun. We will still see partial eclipses, and we might also see annular eclipses where there's still a ring of fire visible around the disk of the moon. So that's in store in something like 1 billion years or so. So again, for those of you who like eclipse chasing and like to see or photograph a total eclipse of the sun, get in now, because it won't happen forever. The moon has a stabilizing influence on the tilt of the Earth. So a second consequence of the moon moving further away is that that stabilizing influence is partly lost. Historically, we know the tilt of the Earth hasn't changed much. The cartoon on the left shows you how much the tilt of the Earth has changed. only a degree or so either side of 23 degrees because of the stabilizing influence of the moon. But if the moon is much further away, then the tilt of the Earth could change erratically, and that of course could result in wild variations in the Earth's climate. Instead of a 23-degree tilt, we might have 0 or 45 degrees or even 90 degrees. There would be very little to stop the Earth's tilt changing dramatically. And that, of course, would be chaos for our climate. Still on a timescale of 10 to the 9 years in the future, the gold disk, which is attached to both of the Voyager spacecraft, will become unreadable. So remember, the gold disc is a sort of a phonograph, if you like, a large LP with a large engraved spiral that gives you audio of people's greetings and music from Earth. Now, how come the Voyager disc lasts so much longer than the Pioneer plaque? They're both going to get degraded ultimately. The metal of which the disk is made is slowly evaporating, and it's been calculated that after 1 billion years or so, the disk will become unreadable. But it will last longer than the Pioneer plaque simply because the disk on the right is protected behind a cover on the left. And it's the cover that's going to take the impact of the interstellar medium. So the cover will become pitted and corroded long before the disk is unplayable. The catch is that the cover on the left actually contains the instructions that tell you how to read the disk on the right. It tells you how fast you should rotate it, and it tells you to put a stylus in the groove, and that will allow you to hear the sounds and the greetings from Earth. But perhaps after 1 billion years, again, it will have passed through tens of thousands of solar systems in this time. If an advanced civilization picks up Voyager before 1 billion years from now, it will be able to read the instructions and play the record. Perhaps if anybody picks it up after 1 billion years, well, they won't have the instructions, but perhaps they'll be intelligent enough to figure it out for themselves. 10 to the 9 years into the future, the Sun is not a red giant yet, but it is changing. As it evolves towards its red giant phase, its luminosity will slowly increase by perhaps 10% every 1 billion years or so. And so on this timescale, the greenhouse effect will drive the surface temperature of the Earth from what it is now to a relatively balmy 80 Celsius. The oceans will boil dry, and it's not clear how we will survive this. Going underground really won't help much. Perhaps we will need to leave the Earth until the red giant phase has passed and the Earth has cooled off a little bit. But as the Sun does become a red giant, its radius will increase substantially, such that its surface approaches the Earth. And you think maybe this could be a problem for us. If the Sun grows large enough such that the radius of the Sun is comparable to the size of the Earth's orbit, it sounds like the Earth is going to get engulfed. Surely that's going to be the end of the Earth. Perhaps, but maybe not, because some people have calculated that the Earth won't necessarily be engulfed by the Sun. Yes, the Sun is going to expand until it's about the size of the Earth's orbit. But as the Sun expands and goes through its red giant phase, there will be very strong solar winds, which result in the Sun losing quite a substantial amount of mass. So if the Sun is less massive, that means less gravitational pull on the Earth, which means the Earth's orbit will actually expand as the Sun slowly grows. So this cartoon on the left shows what might happen. As the Sun gets larger, the Earth actually moves away from its original orbital position. So yes, at some point the size of the Sun will be large enough to engulf the original Earth orbit. But at that point, the Earth's orbit might have increased to the point where it's now where, for instance, Mars currently is. So it won't necessarily get engulfed. It's possible, that the Earth might survive the Sun going through a red giant phase. Once the Sun has been through its red giant phase, it will slough off its outer layers into the interstellar medium to produce a planetary nebula. And what's left will be the core of the Sun, which will be a white dwarf, only about the size of the Earth, but very hot to start with, eventually cooling down. If the Earth survives the Sun going through a red giant phase, it has another problem to contend with many billions of years from now. On a timescale a little less than 10 to the 10 years into the future, the Earth is going to lose its magnetic field. At the moment, the Earth has a magnetic field because its core is molten, and a spinning molten core produces a dynamo effect which generates a magnetic field. The Earth's core is not being kept warm by the Sun, it's being kept warm by radioactive elements that have been in the Earth's core since its formation. But eventually, the decay of those radioactive elements will not produce enough energy to keep the core molten. The Earth's core will solidify, and once it does that, it loses the dynamo, it loses the magnetic field, and it loses the protection that we currently have from the radiation, not so much from the Sun, once the Sun is a white dwarf, but radiation from cosmic rays. It is thought that perhaps this is what happened to Mars. Mars is smaller, its core will have cooled off faster, and if Mars lost its magnetic field a long time ago, it lost its protection, and hence it lost its atmosphere. They say that bad luck comes in threes. If the Earth survives the Sun going through a red giant phase, if the Earth survives the loss of its magnetic field, then shortly thereafter, along comes Andromeda galaxy and crashes into the Milky Way. On a timescale of a few to many billion years, the Andromeda galaxy is going to start to fill our skies, as indicated by this artist's impression. For those of you who like taking pictures of Andromeda, if you wait a few billion years, you won't even need a telephoto lens. A wide-angle lens will be good enough to take pictures of the Andromeda galaxy as it comes our way. As the two galaxies pass through each other, very few stars are going to collide. The galaxies will pass through each other, and there will be a riot of new star formation as the hydrogen clouds of one galaxy impact the hydrogen clouds of a second galaxy. The two galaxies will pass through each other and then eventually settle down into one large galaxy. In this case, the spiral arms have been lost. You can see that we now live in a large elliptical galaxy with no particular spiral arm structure. It's no longer a disk galaxy. And perhaps you can see from this indication here at 5 billion years into the future, there appears to be a couple of nuclei. The two nuclei correspond to what used to be the nucleus of the Milky Way and the nucleus of the Andromeda galaxy, both of which have two supermassive black holes, and those supermassive black holes will continue to orbit each other for quite a few billion years until eventually those supermassive black holes merge into one. That won't necessarily be a problem for the Earth. If the Earth has survived to this point, the Sun may get pulled out of the Milky Way as the Andromeda galaxy crashes into us, but if it does, the planets will simply go with it. It'll be such a slow process that if the Sun does get pulled away by tidal forces, the planets will follow, and so the Earth should survive the impact of the Andromeda galaxy. At 10 to the 11 years in the future, the slow dance between the Moon and the Earth finally comes to an end. The tidal drag of the Moon on the Earth has now resulted in one day being the same as 1 month. In other words, the length of time it takes the Earth to rotate once on its axis is now the same as the length of time it takes the Moon to go once around the Earth in its orbit. The Earth is now tidally locked to the Moon. In other words, if you were in one point on the Earth's surface, the Moon would either be always in your sky or never in your sky. The Moon would not appear to move in much the same way that if you're on the surface of the Moon, the Earth is always in the same point of the sky. One side of the Earth always faces the moon and one side of the Earth never faces the moon. That mirrors what the moon has been doing for billions of years. So at this point, the two bodies become tidally locked to each other, just like Pluto and Charon are at the moment. And this looks like an artist's impression on the right, but no, it's an actual image from the Deep Space Climate Observatory. It only looks odd because the Earth and the Moon are approximately to scale, which you don't often see. And of course, the view of the Moon is the far side of the Moon, which we don't normally see. So it might look like a chocolate digestive biscuit, but it is in fact a genuine picture of the far side of the Moon. On a timescale now of 10 to the 12, 1 trillion years into the future, what's going to happen to the galaxies close to us? Well, if we look at what's happening close to the Milky Way, we have a lot of small satellites around us in the so-called local group, a group of galaxies that are all gravitationally bound to each other. So the Milky Way is one of the largest galaxies, along with Andromeda, and there are dozens, if not hundreds, of smaller galaxies. And we've just seen that Andromeda, M31, is going to crash into the Milky Way. M33 won't be far behind it. And eventually, all of the galaxies in the local group will get absorbed by one large cannibalistic galaxy, which is going to gobble up everything. The entire local group will merge into one mega galaxy. It's not going to be a spiral. That's just an icon to remind us that everything will become one large galaxy. What's happening on slightly larger scales? What about more distant galaxies? Well, at the moment, we know that even galaxies that are receding from us faster than light, for instance, as a lockdown challenge, I tried to image a quasar, the nucleus of a galaxy, which is receding from us at twice the speed of light. And it is possible to image galaxies that are receding from us at those sorts of speeds. Indeed, if we look at the right-hand side, a Hubble Ultra Deep Field, most of the objects you can see in that image are galaxies. All but two of the objects are galaxies. There's 2 stars, lots of galaxies, and most of those galaxies are so remote from us, because of the expansion of the universe, they are receding from us faster than the speed of light. But if we move forward to 10 to the 12 years into the future, the expansion of the universe will take the galaxies so far from us that none of these very distant galaxies will be visible. So if we imagine what would the Hubble telescope see if we turned it on the distant universe in 10 to the 12 years time, the answer is it would see no distant galaxies. It would simply see whatever stars are part of our own galaxy. All of the more distant galaxies are now beyond our horizon. They are so far away, the light will never be able to reach us. And it's interesting to note that if you think of some advanced civilization coming into being 1 trillion years from now, no matter how sophisticated their telescopes, if they trained their telescopes and asked themselves what is in the universe, they would look out into the universe and they would see nothing other than what's in their own galaxy. They would come to the conclusion the entire universe is just our galaxy, because they would have no way of seeing distant galaxies the way we can at the moment, purely as a result of the expansion of the universe. I said 3 years ago, in the beginning of everything, that it took roughly 3 minutes to make all the hydrogen in the universe, and that hydrogen has been fueling all of the stars ever since. We now come to the conclusion that trillions of years later, the hydrogen is running out. If the hydrogen is running out, then that means no new star formation. Now, some people disagree with that. There's a small number of people who say, well, just because you've got no hydrogen doesn't mean you can't make new stars. Is it actually possible to make stars from heavier elements, not from the lightest element, hydrogen, which is what many people believe? Might it be possible to make stars from heavier elements? Calculations indicate that it might be possible to make a star in which there are nuclear reactions occurring at the core, but the surface temperature Remember, for a red giant, the surface temperature might be a few thousand Kelvin. Maybe it's possible to make a star with a surface temperature 10 times less. Maybe the surface temperature might only be hundreds of Kelvin rather than thousands of Kelvin. Is it not possible to make a star in which there are nuclear reactions at the core, but the surface temperature is low enough for ice to form? Frozen stars. Now, no, I'm not talking about Disney's version of frozen stars. If that's the picture you've got in your head, then let it go, because what I'm talking about is stars in which we have nuclear reactions at the core, but ice at the surface. That's a really weird idea, but not everybody agrees that that is actually possible. Most people think that once the hydrogen runs out, you can't make any new stars. Before we can go any further, we need to consider what the expansion of the universe looks like. So let me just draw a quick plot of the size of the universe on the vertical axis as a function of time on the horizontal axis. So there's us now with a size of 1. It's just a relative size. It doesn't matter what the units are. And you can see that there are various models of how the universe might expand and how it might have expanded in the past, according to these 4 coloured lines. The Big Bang occurred at some time in the past, which depends on which coloured line we're actually on. And the coloured lines are a function of how much matter and energy there is in the universe in total. For instance, if the universe contains a huge amount of matter, then that means we would be following the orange curve, and gravity would be able to pull on this matter and stop the expansion and pull it back again into what you might call a big crunch many billions of years into the future. That means the universe would be closed. However, when we look out into the universe and try and work out how much mass is out there, we don't think we're on the orange curve. For a while, we thought we might be on the green curve, meaning the universe was expanding, but the expansion was slowly slowing down. But now it appears that as of 25 years ago, the evidence is that the universe we're in is this one, the red line. A certain amount of matter and energy means that we're on the red curve. And if you look at what the red curve is doing, it's getting larger and larger and larger. The universe is continuing to expand. It doesn't seem to want to come back again. Not only that, but the gradient of the expansion is increasing. In other words, the expansion of the universe is accelerating, it would appear. Trying to understand exactly why that is, well, that's still a little bit of a mystery, but the evidence at the moment is that the universe is not going to collapse in on itself. It's going to continue to expand forever. Let's assume that's the case and move on. We have to change gears now. Notice that all the numbers have now changed because each small box in the timeline now means 1,000,000 times further into the future. Otherwise, this talk would go on all night. So we have to accelerate the speed at which we're moving into the future. So now we're talking about 10 to the power 30 years or 10 to the 48. I don't know what you describe these as. They're simply large, very large numbers. So before we took this little aside about the cosmological model, where did we leave the universe? Well, we said that all the hydrogen is running out after many trillions of years. Now, some stars can last an awful long time. Massive stars don't last long. Less massive stars can live for many, many trillions of years. But they don't last forever. So if the hydrogen is running out, what does that mean? The age of starlight will come to an end. One day There will be no more stars shining. The dead stars will continue to orbit their galaxies. They're no longer shining, but the matter is still there. They're drifting through space like zombies, white dwarfs, neutron stars, black holes. Remember, white dwarf is ultimately the fate of a star like our Sun. More massive stars might end as neutron stars or black holes. White dwarfs will eventually go dark. There are no nuclear reactions keeping them hot. They're not shining. They are simply hot because they were made hot. They are going to cool down, and it won't take them long before a white dwarf is basically a black dwarf, because there is nothing to keep them warm. They will just radiate their heat away. Some stars will be ejected from the galaxy. Some will be eaten by the supermassive black hole, SMBH, that we think is at the centre of every galaxy. Magnetic fields have been mapped out. For instance, this distant galaxy, NGC 1097, the magnetic fields have been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy. That's the 747 with a big telescope in the back. That's now been retired, so watch out on eBay for a 747 for sale at a bargain price. So it's thought that if you map out the magnetic fields, it's thought that matter is funneled by these magnetic fields, and that's the mechanism by which a supermassive black hole will feed on the matter around it. The matter, whether it be stars or the gas from stars, will be funneled into the black hole, basically hoovering up everything in the galaxy. What's going to happen to all the atoms in the universe? Well, our picture of an atom is much like we see on the right-hand side, a nucleus with positively charged protons surrounded by negatively charged electrons buzzing around them. So protons are responsible for the positive charge in a nucleus. But if protons change, if they decay into something else, then that means every atom in the universe will fall to pieces. Now, we don't know whether this will happen, and if it does happen, we don't know the timescale over which it's expected to happen. It's unlikely to be anything less than 10 to the power 36 years, because it looks like protons are stable particles, but we don't know that they will exist forever. Assuming for the moment that protons don't decay, some atoms will survive for a little bit longer. But even black dwarf stars will evaporate through a process I'm not going to describe, and that will leave no atoms in the universe. Remember, neutron stars don't contain atoms, they contain neutrons, and black holes, well, who knows what's in black holes, but it won't be atoms. The black holes, which started life at the centres of massive galaxies, the supermassive black holes will grow to, from perhaps at the moment, our supermassive black hole in the Milky Way is millions of solar masses. Some of the larger galaxies might have supermassive black holes with billions of solar masses. There's no reason why, when galaxies collide with each other and the supermassive black holes merge with each other, there's no reason why these supermassive black holes don't grow until they are trillions of solar masses. But they are not eternal. Black holes do not last forever. According to Stephen Hawking, and many scientists would agree with this, we think that black holes evaporate. You have to wait for an awfully long time, but eventually black holes will evaporate. So what's the process by which this occurs? Well, quantum mechanics, the theory that tells us how things behave on really small scales, tells us that particles and antiparticles can be created by borrowing energy from nothing, effectively. So you basically borrow energy, make some particles and antiparticles, which then annihilate and pay back the loan that you've just taken. You borrow some energy, you make particles and antiparticles, they annihilate and make energy again. That process, energy, particles and antiparticles, back to energy again, that process we believe is going on backwards and forwards all the time. So the question is, how does that relate to the lifetime of a black hole? Well, Hawking said, what would happen if you borrow some energy from just outside the event horizon of a black hole and create particles and antiparticles? one of which goes into the black hole and the other one doesn't. Now they can't annihilate and pay back the loan. It's as if something has come out of the event horizon because it wasn't there before, and now something appears to have come out of the event horizon, strictly from just above the event horizon. So this is what we call Hawking radiation. We haven't observed it yet, but we think it occurs. The radiation increases with decreasing mass. So smaller black holes evaporate quickly, large black holes are very slow to evaporate. That means if we had the patience to watch one, as a black hole evaporates, the radiation levels increase as the black hole gets smaller and smaller and smaller because of the emitted radiation, until it finally disappears in a flash of radiation. Even the largest, even the supermassive black holes, even the ones that are trillions of solar masses lurking at the centres of galaxies, even they will evaporate eventually, though it will take trillions of times longer than for a simple stellar mass black hole. So have we come to the end of time? Well, pretty much. If we think about 10 to the power 100, in other words, a Google, not that one, that's a misspelling of the real Google on the left-hand side. 10 to the power 100 is Google. After a Google years, the last black hole should have evaporated. And from that point onwards, nothing interesting happens. So time becomes essentially meaningless. The universe will continue to expand. There'll be lots of radiation around. The wavelengths of these various photons of radiation will gradually stretch, but there will be no matter left in the universe at all. And just to remind ourselves what a big number 10 to the 100 is, I don't normally add all the zeros in, but in this case, let's just remind ourselves what a Google is. 10 to the power 100 is 10,000 million, yeah, you can do it yourself. It's an awfully big number. Just because it's too large to imagine does not mean it's too large to do calculations of what's going to happen in the future. And that's why we believe 10 to the power 100 is approximately the time at which the last black hole will have evaporated. Eternity is a very long time, especially towards the end, as Woody Allen said some time ago. One of my favourite little quotes from XKCD tries to put a human perspective on the end of the universe. A human, they say, is simply a system for converting dust billions of years ago into dust billions of years from now via a roundabout process, which involves checking email quite a lot. That's one way of thinking of the human perspective of the fate of the universe. But rather than leave you in a rather depressed state telling you that everything is going to come to an end, let me finish with a short epilogue. In a sense, we live in a golden age. The sun is middle-aged and well-behaved. The moon is at just the right distance to stabilise the Earth's axis and hence to stabilise the seasons. And as a bonus, it gives us the spectacle of a total solar eclipse every once in a while. Thanks to evolution, we are able to explore and discover and understand the universe, either by building spacecraft that we send out to visit our closest neighbours, or by building ourselves telescopes that can see within the observable universe trillions of galaxies at distances of billions of light years. We know that humankind could not have arisen in the very early universe because it needed generation upon generation of stars to process the hydrogen into helium, the helium into carbon and nitrogen and oxygen and calcium and phosphorus and all of the heavy elements that were essential for life as we know it to evolve. And as we've just seen, the future, trillions of years from now, the universe will be dark and will be boring. So you could say the best time to exist is now. Thank you for listening.